A world exists where years pass in 18 hours, and the sky holds two setting suns. These are not scenes from fiction, but the documented realities of exoplanets, worlds orbiting stars far beyond our solar system. Today, we will explore 20 such places with conditions more extreme than any science fiction. You will journey to planets made of diamond, worlds evaporating into nothingness, and infernos where metal falls as rain. By the end, you will possess a new understanding of the universe's incredible diversity, challenging everything we thought possible about where and how planets can exist. How did a planet become darker than coal? What does a rain of molten iron sound like on a world of endless storms? The cosmos holds answers that rewrite the rules of reality itself. What do you believe is the strangest thing a world can be? Its very name sounds like a galactic treasure map, 55 Cancri E. This world, a super-Earth orbiting a sun-like star in the constellation of Cancer, is a place of profound extremes. Its incredible density tells the story. While it is only about twice the diameter of our home planet, its mass is over 8 times greater. That immense weight squeezed into a relatively small volume points to a composition unlike anything in our solar system. The leading theory is a staggering one. The core of this world is not molten iron but carbon, compressed under unimaginable pressures into a crystalline lattice. In simpler terms, a significant portion of this planet is likely diamond, but do not picture a tranquil, glittering jewel floating in space. The reality is far more violent. 55 Cancri E orbits its star 25 times closer than Mercury orbits our Sun. A single year there lasts a mere 18 hours. This proximity creates a hellish environment. Surface temperatures are believed to soar beyond 2,000 degrees Celsius, hot enough to melt steel and vaporize rock. The planet is also tidally locked, meaning one side forever faces the star's blistering glare, while the other is shrouded in eternal night. The day side is not a solid diamond crust, but a global, churning ocean of lava, with the very carbon of the surface simmering into a sea of molten graphite. The night side, while cooler, is still unimaginably hot by our standards, and might feature a landscape of solidified carbon structures. This glittering inferno forces us to rethink the ingredients of planets. Our solar system is oxygen-rich, leading to rocky worlds like Earth, but 55 Cancri E hints at an entirely different recipe, one where carbon is the dominant element. Its existence proves that under the right stellar conditions, worlds of pure elemental treasure can be forged. It is a monument to cosmic alchemy, a diamond born not in peace but in fire. If such a world can exist, what other impossible substances might form the bedrock of distant planets? While one world forms from cosmic pressure, another is actively dissolving into the void. HD 209,458b, known by the evocative nickname Osiris, presents a spectacle of planetary evaporation. This is a hot Jupiter, a gas giant, but it orbits its star at a distance 1/20th that of Mercury from our Sun. The stellar radiation it endures is so ferocious that it does not merely heat the atmosphere, it violently strips it away. Imagine a constant, supersonic solar wind scouring the planet's outer layers, tearing billions of tons of gas into space every second. This creates a vast, comet-like tail of hydrogen and other elements that stretches for millions of kilometers behind the fleeing world. For the first time, astronomers did not just theorize about this process, they watched it happen. By analyzing the starlight filtering through this escaping cloud, they measured the gases streaming away at speeds exceeding 35,000 kilometers per hour. It is a real-time observation of a planet's slow dissipation. Osiris is not a stable, eternal sphere. it is a temporary structure in a losing battle with its star. This transforms our view of planetary systems from still portraits into dynamic movies. Worlds are not simply born and then exist unchanged. They are engaged in a constant physical dialogue with their suns, sculpted by gravity and radiation. Some, like Osiris, are being sculpted into oblivion. Its grand, glowing tail is both a beautiful astronomical phenomenon and a funeral shroud, a stark reminder that in the cosmos, even giants are not permanent. It forces a profound question. If we see a planet today, does that guarantee it will be there in 1,000,000 years? Or are we merely catching a fleeting glimpse of a celestial story already nearing its end? The cosmos holds not only worlds of crushing density, but also those of astonishing lightness. Meet WASP 107b, a planet that defies every intuition about how solid a world should feel. If Jupiter is a dense, muscular ball of gas, this world is its ethereal ghost. It is nearly the same size as our solar system's giant, yet it possesses less than 1/10 of Jupiter's mass. To grasp its composition, picture not a swirling gas giant, but something far more delicate, its density comparable to a block of styrofoam floating in a cosmic sea. Astronomers call these super puffs or cotton candy planets, and WASP 107b is one of the fluffiest we have ever found. Its atmosphere is a vast, extended shroud of hydrogen and helium, so diffuse and bloated that the planet seems to barely hold itself together. This presents a profound mystery. The planet orbits incredibly close to its star, completing a year in just under 6 Earth days. At that distance, the stellar radiation should be violently stripping away that puffy atmosphere, much like it does to Osiris. Yet the cotton candy world persists. How does it retain its delicate form against the stellar wind? One compelling theory points to an internal furnace. The planet's unusual orbit might create intense gravitational flexing, generating tremendous internal heat that puffs the atmosphere up from within, like a balloon being filled. Another possibility is a surprisingly small, rocky core at its heart, around which an immense but lightweight envelope of gas somehow accumulated. This world challenges the very definition of a planet, stretching our categories to their breaking point. It demonstrates that planetary structures are not just variations on a theme, but can represent entirely different genres of cosmic object. The existence of such a fragile giant hints at formation histories we are only beginning to imagine, where gentle processes can assemble something as large as Jupiter, but as light as a dream. If a planet can be made of styrofoam, what other impossible textures might the universe have sculpted? Kelt 9b does not merely orbit a star, it endures one. This ultra-hot Jupiter circles a blue Type A star that burns at nearly 10,000 degrees Celsius, and it does so with terrifying intimacy. A single year on this world passes in less than 1.5 Earth days, a frantic sprint through an unthinkable furnace. The dayside temperature soars beyond 4,300 degrees Celsius, a heat that surpasses the surface of many red dwarf stars. At this threshold, the very concept of planetary chemistry shatters. Molecules cannot survive. Water, carbon dioxide, even hardy titanium oxide are ripped into their individual atoms by the relentless energy. Elements like iron and titanium do not pool or form minerals. They exist as vapor, swirling in an atmosphere that behaves more like the outer layers of a star than any environment we would recognize. This world is so profoundly hot that it glows with its own fierce, violet-hued light. It is a planet being unmade by its own sun, its atmosphere constantly boiling away into space, much like Osiris, but at a far more catastrophic scale. The planet is also tidally locked, presenting one face to the stellar fury for all eternity. The dayside is a single, global hurricane of incandescent gas, while the night side, though shielded from direct light, is still scorching beyond imagination, heated by supersonic winds that carry the day's thermal violence around the globe. Kelt 9b is less a traditional world and more a cosmic experiment, a natural laboratory that shows us the absolute limit of what we can call a planet. It exists in a zone where the rules of stellar and planetary physics blur, teaching us that under enough pressure and radiation, the familiar building blocks of matter behave in utterly alien ways. If a place like this can exist, it forces us to wonder what is the true boundary between a planet and a star. But the search for life leads us not only to infernos, but to a world of profound and delicate contrasts. Proxima Centauri b is our nearest exoplanetary neighbor, a rocky world orbiting the red dwarf star closest to our Sun. It resides within what astronomers call the habitable zone, the orbital band where temperatures might allow for liquid water. Yet this promise of potential is shaped by an extreme condition. The planet is almost certainly tidally locked, with one hemisphere forever bathed in the dim, crimson light of its star, and the other plunged into an eternal, frozen night. This creates what scientists term an eyeball planet. Picture a world where the dayside, under constant stellar gaze, could host a vast, single ocean of liquid water simmering beneath a stationary sun. The night side, meanwhile, would be a global ice cap, a deep freeze locked in permanent shadow. Between these two absolute realms lies the most intriguing place of all, a thin, circular strip of perpetual twilight. Here, the sun forever hangs on the horizon, creating a band of potentially temperate climate caught in an endless dusk. This twilight ring could experience weather patterns unlike anything on Earth, with howling winds racing from the hot side to the cold, driving precipitation in a never-ending cycle. It is a world of stark geographical duality, where your entire climate is determined not by the season, but by your permanent address. Yet the hope for a watery oasis is tempered by a brutal reality. Red dwarf stars like Proxima Centauri are notoriously volatile, prone to violent eruptions called stellar flares. These flares can unleash torrents of X-rays and ultraviolet radiation, bathing the planet's surface in levels that could strip atmospheres and sterilize the ground. Proxima Centauri b thus stands as a powerful symbol in our search, embodying the extreme tension between possibility and peril. It is a world that could, in theory, cradle a liquid ocean, yet must constantly endure the fury of its own sun. This forces us to expand our definition of habitable. It is not just about distance and temperature, but about a planet's resilience, its ability to shield itself or its life from the cosmic elements. If life were to exist on such a world, where would it find refuge? Would it cling to the sunlit ocean, adapt to the deep ice, or thrive in the dynamic, crepuscular border between fire and frost? The forecast on WASP 76b calls for a perpetual metallic downpour. This ultra-hot Jupiter takes the concept of extreme weather into a realm of pure spectacle. Orbiting perilously close to its star, its dayside temperature exceeds 2,400 degrees Celsius, a heat so profound it does not merely melt rock, it vaporizes metals. Elements like iron are torn from the surface and lifted into the atmosphere, not as dust but as a shimmering, incandescent vapor. Here is where the planet's true drama unfolds. The searing dayside and the cooler, though still hellishly hot, night side create a titanic pressure difference. This drives supersonic winds that race across the terminator, the dividing line between eternal day and eternal night, carrying the vaporized iron with them. As this metallic cloud crosses into the relative chill of the night side, something astonishing happens. The iron condenses, it forms droplets, and then it falls. The sky rains molten iron. Picture a global storm where the precipitation is not water, but a luminous, liquid metal streaming through an atmosphere of alien chemistry. Astronomers confirmed this not through theory, but by direct observation. By studying the starlight filtering through the planet's atmosphere at different points in its orbit, they detected the clear signature of iron vapor on the blistering day side, but found it noticeably absent on the night side. The most logical explanation: the iron had literally rained out. This world transforms abstract climate models into a breathtaking, observed reality. It shows us that planetary weather is not confined to the water cycles we know, but is a universal physical process that can work with any substance, given the right extreme conditions. The metallic deluge on WSP-76b is more than a curiosity. It is a masterclass in cosmic chemistry and fluid dynamics, painting a vivid picture of how matter moves and transforms on a scale and in a manner we are only beginning to comprehend. What other elemental storms might lash the skies of distant worlds, where the very air can turn to stone or the clouds be woven from glittering silica? T7b is a world that has been distilled down to its most brutal essence. This super-Earth, a rocky planet larger than our own, does not merely orbit its star, it clings to it in a death spiral. A single year there passes in just 20 hours, a frantic orbit that brings it staggeringly close to its sun. The resulting heat is beyond terrestrial comprehension, with dayside temperatures soaring above 2,000 degrees Celsius. At that threshold, the very ground cannot exist. Silicate rock, the foundation of continental crusts on Earth, does not simply soften, it liquefies completely. The surface of T7b is not a landscape of mountains and valleys, but a single, churning, global ocean of lava, hundreds of kilometers deep. It is a planet with a molten skin, a sphere of perpetual, incandescent fury. This leads scientists to a startling hypothesis about its origin. T7b may not have been born this way. Its immense density suggests it could be the naked, scorched core of a former gas giant, a planet like Jupiter or Saturn that once possessed a vast, billowing atmosphere. But as it migrated inward, the relentless stellar radiation and solar wind would have acted like a cosmic sandblaster, stripping away the hydrogen and helium envelope layer by layer over eons, until only the dense, rocky heart remained, exposed to the stellar furnace. Today, its atmosphere, if it can even be called that, is a thin shroud of vaporized rock, minerals like sodium and potassium boiled off from the lava ocean below. This world stands as a stark monument to the destructive power of a star. It shows us a possible endpoint for planetary evolution, a grim fate for worlds that wander too close. T7b is a planetary phoenix that will never rise from its own ashes, forever trapped in a state of elemental chaos, reminding us that in the cosmos, even a giant can be reduced to its core and forced to burn. The sky over Kepler 16b holds not one but two setting suns. This Saturn-sized world does not orbit a single star, but a pair locked in their own gravitational embrace, making it the first confirmed circumbinary planet. Its discovery transformed a beloved science fiction image, the twin suns of Tatooine, into a documented astronomical reality. Here, the planet circles both stars, tracing a wide, stable path around their shared center of mass. The stellar duo consists of a smaller, cooler red dwarf and a larger, sun-like star, each casting its own distinct hue across the alien landscape. From the surface, the cosmic ballet would be a spectacle of constant change. Some days, the stars would eclipse each other, casting complex, shifting shadows. Other times, they would set together in a breathtaking double sunset, or rise apart, stretching the dawn across a dramatically extended twilight. This celestial dance creates a climate of profound complexity. The planet receives a constantly varying amount of light and heat as the stars move closer and farther from each other in their own orbit. Gravitational tides from both suns would pull and flex the world in intricate rhythms, potentially stirring its atmosphere and interior in ways no single star could. The discovery of Kepler 16b shattered a long-held assumption about planet formation. Astronomers once doubted that the chaotic gravitational environment of a binary system could allow planets to coalesce and maintain a stable orbit. This world proved them wrong. Its existence flung open a new door in the cosmic search, revealing that binary and even triple star systems are not planetary deserts, but fertile new frontiers. It dramatically expanded the potential real estate for worlds in our galaxy, suggesting that millions more planets could exist in these once overlooked neighborhoods. Kepler 16b stands as a powerful symbol of science catching up to imagination, a place where the sky itself performs a perpetual, silent duet, reminding us that the universe often crafts realities more wondrous than our most creative stories. If stable planets can form around two stars, what other familiar scenes from fiction might be waiting for us in the data? TESS-2b is a shadow in space, a world that swallows light. This hot Jupiter holds the ominous title of the darkest exoplanet we have ever found, reflecting less than 1% of the starlight that falls upon it. It is blacker than coal, darker than fresh asphalt, an orb of profound and puzzling darkness orbiting a star not unlike our Sun. The planet is searingly hot, orbiting incredibly close, yet its atmosphere refuses to shine. While most hot Jupiters, like Kelt 9b, blaze with their own fierce glow, TESS-2b is a cosmic silhouette, a void against the stellar backdrop. The secret likely lies in its alien chemistry. Its atmosphere is thought to be a brew of exotic, light-absorbing vapors, perhaps vaporized sodium and potassium, or clouds of titanium oxide, all substances that capture photons rather than scattering them back into space. Yet even the best chemical models cannot fully explain the planet's utter blackness. It is a deeper dark than any simple ingredient list can account for, suggesting a more complex and mysterious atmospheric alchemy at work. Despite its shadowy nature, it is not a cold place. Its dayside temperature soars above 900 degrees Celsius, and it glows faintly with a deep, dim, red heat of its own emission, like a banked coal in a cosmic fireplace. This combination makes it an enigmatic paradox, a world both dark and intensely hot, absorbing nearly all energy yet still radiating a feeble warmth. Its existence challenges fundamental ideas about planetary atmospheres and albedo, the scientific term for reflectivity. We are forced to ask what processes can create a gas giant that is essentially a perfect absorber. Is its atmosphere somehow devoid of the reflective clouds we see on Jupiter, or is it structured in a way that traps light within endless layers? TESS-2b is more than a curiosity. It is a profound puzzle that probes the limits of our understanding, a reminder that in the cosmos, even something as simple as darkness can hold layers of deep and unresolved mystery. What other unseen properties might be hiding within the atmospheres of worlds we have only begun to catalogue? Beneath a thick, perpetual haze lies a world not of fire, but of profound and pressurized deep. GJ1214b is a cosmic enigma, a planet caught between categories, larger than Earth but smaller than Uranus, with a density so low it cannot be made of rock alone. Its true nature is hidden beneath a global shroud of clouds or steam, but the numbers point to a composition dominated by one of the universe's most common substances, water. This is not a water world as we might dream of it, with sunlit waves breaking on sandy shores. The reality is far stranger and more extreme. The planet's immense mass creates gravity that squeezes its contents with unbelievable force. Here, the very idea of water transforms. At the bottom of what might be a planet-wide ocean, tens or hundreds of kilometers deep, the pressure is so great that water cannot exist as a simple liquid. It is forced into exotic, alien phases scientists call hot ice or superfluid water. Hot ice, known as Ice 7, is a crystalline form that remains solid at temperatures that would boil water on Earth, all because the crushing pressure locks the molecules into a rigid structure. The ocean itself could behave as a superfluid, a liquid with almost no friction, flowing with eerie efficiency. There may be no coastline, no beach, no solid surface at all. An astronaut descending into its atmosphere might pass through layers of thick mist and steam, then into a perpetual, global rain, falling into an ocean that grows denser and stranger with every meter descended, finally reaching depths where the water itself takes on the properties of a solid, all while remaining scalding hot. This world illustrates a fundamental truth of the cosmos. An element as familiar as H2O is not defined by the calm, life-giving form we know. Under the extreme pressures found inside giant planets, it becomes something entirely other, a substance with the rules of physics rewritten by force. GJ1214b is a reminder that the universe often hides its greatest marvels not in fire, but in the silent, crushing deep, where even the most essential compound for life as we know it becomes an agent of alien geology. Drifting through the absolute cold and silence between stars, a world exists without a sun. SIMP J01365663 plus 09333473 is a cosmic nomad, a planetary mass object untethered from any stellar anchor, wandering the interstellar void. This places it in a fascinating category that blurs the lines, a rogue planet with the characteristics of a failed star. It is massive enough, about a dozen times the size of Jupiter, to still retain a fierce internal heat from its violent formation billions of years ago. This remnant glow provides a faint, dusky warmth, but its surface remains a profoundly frigid landscape with temperatures around 800 degrees Celsius. While that sounds scorching in the context of space and compared to the infernos of close orbiting worlds, it is a deep, radiating chill. The true spectacle, however, is not its temperature but its invisible force. This object possesses a magnetic field over 200 times stronger than Jupiter's. This colossal magnetosphere, interacting with charged particles in the sparse interstellar medium or possibly even particles from an orbiting moon, generates something astonishing: auroras. Picture the scene, a world of eternal and perfect night. Above a dark, rugged landscape, the sky explodes in silent, colossal curtains of shimmering light, dancing with colors unseen on Earth, powered entirely by the planet's own internal dynamo. There is no sunrise to herald a new day, only the perpetual, lonely glow of geological heat and these self-made celestial fireworks. The existence of such wanderers forces a profound rethink. If a planet is defined by orbiting a star, what do we call these solitary travelers? They represent an entire hidden population of worlds, cast out from their birth systems by gravitational chaos or forming alone in the dark. Their silent journey through the galaxy's empty stretches represents the ultimate form of isolation, a testament to the fact that planetary existence does not require a sun, only mass, gravity, and a story that begins and ends in the dark. How many more of these lonely, self-illuminated worlds are passing through the blackness, their auroral lights unseen by any eye? 16 hours is all the time this world has for a year. TOI 2109b is an ultra-hot Jupiter in a state of frantic terminal velocity, orbiting so close to its star that a full celestial revolution passes in less than a single Earth day. This is not a stable, eternal path, but a death spiral. The gravitational tides between the planet and its star are immense, constantly sapping energy from the planet's orbit and causing it to inch closer with every frantic loop. It is a world living on borrowed time, offering astronomers a rare, real-time view of a planet's final act before it is consumed. The proximity creates almost unimaginable conditions. The dayside temperature is estimated at 3,500 degrees Celsius, a furnace where molecules are torn apart and metals exist only as vapor. But the violence is not just thermal, it is physical. The gravitational pull from the star is so powerful it doesn't just hold the planet in orbit, it actively distorts its shape. This world is not a perfect sphere, it is stretched slightly egg-shaped by the relentless tidal forces, a permanent gravitational grip warping its very structure. We are witnessing a cosmic process of tidal disruption in its intermediate stages, a dance that will inevitably end in the planet's destruction, either by being ripped apart or plunging into the stellar atmosphere. This transforms TOI 2109b from a mere planet into a cosmic clock, ticking down toward an inevitable conclusion. Its existence allows scientists to test theories about orbital decay and planetary migration with unprecedented precision, studying how giants meet their end. It is a stark reminder that planetary systems are dynamic and often violent theaters, where orbits are not fixed tracks but narratives with beginnings, middles, and ends. This world's 16-hour year is counting down, a fleeting heartbeat in the lifetime of a star, showing us that even the largest planets are not permanent fixtures, but temporary guests in a gravitational arena. Our own solar system holds a frozen oracle of what might await us around distant stars. Saturn's moon Titan is a world with rivers, lakes, and a thick atmosphere, but its chemistry is a cryogenic echo of Earth. The rivers are liquid methane, the dunes are hydrocarbon sand, and the temperature is a staggering -180 degrees Celsius. Now, take that entire concept and scale it up to a full-sized planet orbiting a cool, dim red dwarf star. This is not yet a confirmed discovery, but a compelling prediction, a hypothetical exoplanet that would be a super-Titan. Its atmosphere would be a dense shroud of nitrogen, perhaps with methane clouds drifting through an eternal, hazy twilight. The landscape below would be utterly alien, yet hauntingly familiar. Vast, dark dunes of organic sand, sculpted by slow, frigid winds, could stretch to the horizon. And cutting through those dunes, river valleys and shorelines would trace the flow not of water, but of liquid methane and ethane, pooling into great, mirror-smooth lakes under a dim red sun. This is a world where the very definition of a solvent, the liquid that facilitates chemistry, is rewritten. On Earth, water is that magical medium. On a super-Titan, the role is played by liquid methane, flowing at temperatures hundreds of degrees below zero. In that profound cold, a rich and complex organic chemistry could still unfold, molecules linking and reacting in the sluggish, frigid flows, potentially creating the prebiotic building blocks for life. But it would be a life unlike any we can readily conceive, one that breathes a nitrogen atmosphere and uses liquid hydrocarbons the way we use water. This hypothetical extreme is a powerful mental tool. It shatters the Earth-centric bias of the habitable zone, forcing us to consider that biology might not need a yellow sun and a temperate climate. It expands the search into the realm of cryogenic chemistry, where the spark of life, if it exists, must ignite and persist in a deep freeze. Such a world would be a frozen mirror to our own, reflecting the same processes of erosion, weather, and perhaps even prebiotic evolution, but cast in entirely different materials. If we one day find this methane dune world, it will not just be a new planet, it will be a new philosophy, proving that life's potential is not bound to our familiar, warm, and watery corner of the universe. But some wanderers are not failed stars, they are silent stones. The interstellar object Oumuamua was our first visitor from another star, a tumbling shard of rock or metal that passed through our solar system on an unstoppable hyperbolic path. Its brief appearance ignited a profound realization. Other star systems are not closed gardens. They can violently eject fragments of themselves, casting geological shrapnel into the galactic sea. Now extrapolate that idea to its ultimate scale. What if the ejected object is not a mere asteroid, but an entire planetary body? Imagine a dwarf planet, or perhaps the shattered core of a larger world, hurled from its home by a gravitational cataclysm. This would be a hyperbolic comet planet, a true cosmic nomad on a one-way journey between the stars. Its environment would be the most extreme isolation imaginable. Far from any stellar warmth, its surface temperature would plummet toward absolute zero, the point where all molecular motion nearly ceases. Any atmosphere it once possessed would have long ago frozen into a solid, glacial crust, coating its surface in a permanent, airless frost. There is no sunrise, no seasonal change, only the perpetual and perfect cold of the interstellar deep. Yet within that frozen silence lies an incredible scientific treasure. This world would be a pristine geological time capsule, an unaltered record of the ancient solar system that forged it. Its composition, its isotopes, the very structure of its material would tell a story untouched by stellar winds or planetary migration, carrying the chemical signature of its birth across light years. To study such a traveler would be like opening a letter sent from a distant galactic neighborhood billions of years ago, offering clues about planetary formation processes we can never witness directly. These hypothetical worlds represent the ultimate travelers, not just drifting through space, but actively crossing the immense voids between stars. They are silent ambassadors from alien origins, reminding us that the building blocks of solar systems are not forever bound to their suns, but can be sent on epic, million-year journeys, carrying the history of lost worlds into the eternal night. What other fragments of alien geology might be sailing past us right now, invisible in the dark? The heat that shapes a world need not come from a star. Imagine instead a rocky planet caught in a gravitational tug-of-war between a nearby gas giant and perhaps other moons in a crowded system. This is the principle behind a hypothetical Io-like exoplanet. In our own solar system, Jupiter's moon Io is the most volcanically active body we know, its surface dotted with hundreds of erupting vents, all because of the immense tidal forces from Jupiter and its sibling moons. These gravitational pulls constantly stretch and squeeze Io's interior, generating friction and heat through a process called tidal heating. Now, scale that up to a full-sized rocky planet orbiting close to a hot Jupiter or locked in a complex dance within a binary system. The result would be geological chaos. The planet's interior would be a roiling furnace of molten rock, not from radioactive decay alone, but from this relentless gravitational kneading. The crust would be thin, fragile, and constantly shattered. Lava would not erupt from occasional volcanoes. It would flood the landscape from countless fissures, creating vast, interconnected lakes of molten rock that glow across entire continents. The atmosphere would be a toxic, ever-changing shroud, continuously belched from these global eruptions, a mix of sulfur dioxide and volcanic ash that might rain back down as acidic precipitation. This is a world where the very ground beneath your feet is temporary. Mountain ranges could rise from volcanic flows in a matter of years, only to be swallowed by a new lava sea a decade later. The entire surface could be recycled on a human timescale, making it a planet with no permanent geography, only an ever-shifting map of fire. Such an extreme demonstrates a fundamental cosmic truth, that energy to drive a world's engine can come from motion and gravity as powerfully as from starlight. It presents a vision of a planet as a perpetual motion machine of geology, its heart fired not by a distant sun, but by the relentless, rhythmic pull of its celestial neighbors. If life against all odds could emerge in such a place, where would it find a foothold in a landscape that refuses to stay still? Beyond the realms of observed reality lies a world built from pure speculation. Pushing into theoretical extremes, scientists imagine planets born from disks of carbon so rich that oxygen, the foundation of our rocky Earth, becomes a scarce afterthought. In such a stellar nursery, the chemistry of planet formation takes a radical turn. The result would not be a world of granite and basalt, but of graphite and diamond. Its crust could be a thick, dark layer of graphite, the same material in a pencil lead, but on a planetary scale. Beneath that, under pressures we can scarcely calculate, that carbon would crystallize into a mantle of solid diamond, hundreds or even thousands of kilometers deep. Yet the strangeness might not stop there. With silicon also present, the surface could be forged from silicon carbide, a material harder than most gems, known on Earth as the abrasive moissanite. This would create a landscape of incredible durability, a planet where mountains are not worn down by wind and water, but stand for eons against a star's glare. In the most imaginative scenarios, geological processes we cannot yet model might craft natural megastructures, continent-sized crystalline formations that emerge from the diamond deep. Picture vast geometric mountain ranges that are not jagged peaks, but faceted, monolithic spires of perfect crystal, refracting the starlight into impossible rainbows. While no such world has been confirmed, its theoretical possibility serves a crucial purpose. It shatters the last remnants of Earth-centric thinking in planetary science. Our solar system provided a single recipe book, but the galaxy's pantry is unimaginably vast. By daring to conceive of a carbon megastructure world, we are forced to admit that the very ground beneath a planet's sky could be made of substances we consider precious or industrial, arranged on a scale that makes terrestrial geology seem fragile and temporary. This speculative frontier is not mere fantasy. It is a vital exercise in material imagination, reminding us that until we look, we cannot truly know what is impossible. What other unthinkable bedrock might await discovery, where the very continents sparkle with a cold, celestial light? The clear skies of HTP 11b are a gift to astronomers, offering a view into the soul of a distant world. This Neptune-sized planet, orbiting incredibly close to its star, possesses an atmosphere that is both swollen and remarkably transparent. Unlike the thick, cloudy veils of our own Neptune, observations suggest its upper skies are often clear, with few high-altitude clouds to block our view. This clarity allows telescopes to peer deep into its chemical makeup, detecting the unmistakable signature of water vapor swirling within its gaseous layers. But this transparency comes at a cost. The intense stellar heat causes the planet's atmosphere to puff up like a balloon over a flame, expanding to a size much larger than expected for a world of its mass. This extended, tenuous envelope is under constant assault, likely bleeding molecules into space in a steady, evaporative stream. HTP 11b occupies a crucial middle ground in planetary science, acting as a key laboratory. It sits in the poorly understood gap between dense, rocky super-Earths and the cold, icy giants like Neptune and Uranus. By studying its puffy, clear atmosphere, we gain vital clues about how planets of this mysterious class form and evolve. Is it a mini-gas giant that formed farther out and migrated in, now slowly cooking away? Or is it a super-Earth that managed to accumulate a vast primordial atmosphere it can no longer fully hold onto? Each molecule we detect in its clear skies helps answer these questions, revealing the dynamic processes that shape warm, gaseous worlds. This world reminds us that a planet's atmosphere is not a static shell, but a dynamic and vulnerable frontier, a buffer between the planetary interior and the void, one that can be inflated, stripped away, and made brilliantly clear by the relentless light of its sun. A planet can rebel against the very spin of its own sun. WSP-17b is a world that moves backward, tracing a retrograde orbit that defies the fundamental expectations of an orderly solar system. In our own celestial neighborhood, every planet dutifully follows the direction of the sun's rotation, like marbles rolling along the same groove on a spinning plate. This consistency is a fossil of the system's birth, a record of the original cloud's spin. But WSP-17b does the opposite. It orbits in the reverse direction, moving against the current of its star's spin. This is not a minor quirk, it is a profound anomaly that points to a deeply violent past. Such a dramatic orbital flip does not happen through gentle nudges. The most likely explanation is a gravitational catastrophe in the system's youth, a close encounter so powerful it literally threw the planet's path end over end. Perhaps a near collision with another giant planet, or the gravitational tug of a passing star in the system's crowded early days, acted like a cosmic slingshot, violently reversing the world's course. The planet itself is another of those low-density, puffy hot Jupiters, bloated by the intense heat of its close orbit, but its physical form is secondary to the story written in its motion. Its backward journey is its defining, revolutionary extreme. The discovery of this retrograde rebel sent shockwaves through planetary science. It upended the classical, tidy model of system formation that was based largely on our own solar system. WASP-17b is living proof that planetary systems are not always neat, concentric, and orderly. They can be arenas of gravitational chaos, where worlds are tossed, flipped, and rearranged in dramatic events that leave permanent scars on their orbits. This single world forces us to accept that a stable-looking system we see today might be the calm after a storm, a peaceful configuration that hides a history of incredible violence. It is a testament to the dynamic, often tumultuous processes that shape planetary families, reminding us that the cosmos favors not just order, but also the enduring echoes of beautiful, disruptive chaos. 7 worlds move in perfect cosmic rhythm. The TRAPPIST-1 system presents an extreme not of fire or ice, but of profound celestial harmony. Orbiting a small, cool red dwarf star, these 7 roughly Earth-sized planets are locked in an intricate gravitational ballet known as orbital resonance. Their orbits are not random distances apart, but are synchronized with mathematical precision. For every 8 orbits the innermost world completes, the second planet completes 5, and the third completes 3. This precise chain of ratios continues out through the system, linking all 7 worlds in a stable, repeating pattern. It is a solar system that functions like an immense, self-correcting clockwork, each world's gravity gently nudging the others to keep the perfect time of their orbits. This resonant arrangement creates a gravitational environment of constant, gentle interaction. As the planets swing past one another in their tight orbits, they pull on each other with a rhythmic force. This could have profound effects, potentially flexing their interiors to generate heat through tidal forces, much like the hypothetical Io world, but on a gentler, system-wide scale. This internal warmth might help maintain subsurface oceans, even on worlds that receive little stellar heat. The resonance also provides a gift to astronomers. Because the orbits are so perfectly aligned from our vantage point, each planet transits or passes in front of its star with predictable regularity. This allows us to study their atmospheres, measure their sizes and masses with incredible accuracy, and confirm that they are all rocky worlds, making this the largest known family of Earth-sized planets we have ever found. Several of these siblings orbit within the star's habitable zone, that region where liquid water could exist. Yet the promise of this delicate clockwork is tempered by the nature of its heart. The red dwarf star is prone to violent flares, eruptions that could bombard the closely packed planets with sterilizing radiation, potentially stripping away atmospheres over time. This creates a central tension for the possibility of life. Could the rhythmic gravitational heating protect subsurface oceans? Could magnetic fields, forged by that same tidal heating, shield the surfaces? The TRAPPIST-1 system is a unique laboratory. It allows us to study 7 worlds born from the same material, under the same star, but occupying different positions in the resonant chain and receiving different levels of light and heat. By comparing them, we can learn how subtle changes in distance and gravitational environment create wildly different planetary outcomes. It is a masterclass in comparative planetology, a demonstration that sometimes the greatest extreme is not chaos, but an almost impossible, enduring order. The final world in our journey offers a vision of elemental apocalypse made permanent. K2141b is a rocky super-Earth locked in a state of perpetual, violent transformation. Its surface is not land, but a single, churning ocean of magma, hundreds of kilometers deep, stretching across the entire day side of the planet. This world is so close to its star that its surface temperature exceeds 3,000 degrees Celsius, a heat so intense the solid ground simply cannot exist. The molten rock glows with its own fierce, orange-white light, a beacon of geological fury in the dark. But the true horror and wonder of this place is not just the lava, it is the weather. At these temperatures, the rock itself boils. The planet's atmosphere is not made of gases we would recognize, but of vaporized stone, a swirling fog of sodium, silicon monoxide, and silicon dioxide. This is a sky where the clouds are literal rock vapor. The cycle completes with a terrifying precipitation. Powerful, supersonic winds, born from the extreme temperature difference between the eternal day and eternal night, carry this mineral atmosphere to the frigid, dark side of the world. There, in the profound cold of permanent shadow, the vapor condenses. It forms droplets and then it falls. The sky rains liquid rock, a silicate downpour that streams back into the global magma sea, only to be evaporated once more by the dayside's fury. This creates a complete, self-contained cycle of evaporation and precipitation, a water cycle of the underworld, where the roles are played by molten and vaporized stone. It is a world where the very concept of ground is an illusion, a temporary state in an endless thermodynamic loop. K2141b stands as a stark and fitting conclusion, a monument to the raw, transformative power of stellar proximity. It shows us that on the cosmic scale, the familiar processes that give Earth its rivers and clouds are not unique. They are universal templates that can be executed with any material, under any condition. The universe does not just create strange worlds, it engineers entire systems of alien meteorology, where the air can be stone and the rain can be fire. Our tour of extremes ends here, not with a whimper, but with the roaring, glowing spectacle of a planet turning itself inside out, over and over again, forever. These worlds of diamond and iron rain exist as more than just theoretical possibilities. They are documented realities. But how can we possibly know the composition of a planet we will never visit, one that is a mere speck of light lost in the glare of its own star? The answer lies in a symphony of ingenious techniques, each allowing us to listen to the faint whispers of distant solar systems. The most prolific method is the transit. Picture a world passing directly between its star and our telescopes. For a few hours, it casts a tiny but measurable shadow, causing the star's light to dim by a minuscule fraction. This simple dip in brightness reveals the planet's size and its orbital period, the length of its year. But the real magic happens when that starlight filters through the planet's atmosphere on its way to us. This is where spectroscopy transforms a shadow into a story. By splitting that filtered light into a rainbow spectrum, astronomers can read the chemical fingerprints of the gases the light has passed through. A specific missing color indicates the presence of water vapor, sodium, or even vaporized iron, painting a portrait of an alien sky. Another crucial technique listens for the star's wobble. A planet's gravity does not just keep it in orbit, it also tugs on its star, causing it to shift subtly back and forth. This radial velocity method measures the star's slight dance, revealing the planet's mass. Combine the mass from the wobble with the size from the transit, and you get density, telling you if a world is a puffy gas giant, a dense rocky sphere, or a diamond. Direct imaging is the most challenging feat of all, like trying to photograph a firefly next to a brilliant searchlight from miles away. Advanced instruments called coronagraphs physically block the star's blinding glare, allowing the faint, reflected glow of the planet itself to be seen. This provides precious details about its temperature and atmospheric conditions. These methods are empowered by a fleet of cosmic sentinels. The Kepler Space Telescope stared at one patch of sky for years, discovering thousands of worlds by watching for their transits. Its successor, TESS, now scans almost the entire sky, hunting for planets around our nearest stellar neighbors. And the James Webb Space Telescope, with its unparalleled sensitivity, is now performing detailed spectroscopy on exoplanet atmospheres, searching for the signatures of molecules that could hint at alien chemistry or even biological activity. The true wonder, then, is not just that these extreme worlds exist. The profound revelation is that from our tiny, pale blue dot, we have learned to measure the wobble of a star 100 light-years away, to weigh a planet made of diamond, and to detect the scent of vaporized rock in an atmosphere we will never breathe. Our greatest achievement is not the discovery itself, but the brilliant, patient light we have learned to read. Diamond planets and iron rains are more than cosmic spectacle. They are profound scientific statements. Each rogue nomad drifting in the dark and each world locked in a resonant chain is a direct challenge to the textbooks, forcing us to rewrite the rules of what a planet can be. Our own solar system, once the only model we had, is now understood to be just one quiet example in a vast and riotous gallery of planetary designs. This is the true legacy of these 20 worlds. They have stretched our imagination not by abandoning science, but by revealing its full, breathtaking scope. The universe is a laboratory operating on a galactic scale, and we are only beginning to read its results. With every new telescope, like the James Webb and the enormous observatories being planned for Earth and space, we peer deeper into this cosmic workshop. We will undoubtedly find environments even more extreme, more bewildering, and more beautiful than anything we have yet conceived. They will ask new questions we cannot yet even form. So let this exploration serve as a reminder. The night sky is not a static tapestry, but an ongoing story of creation and transformation, written in the language of physics and chemistry on a canvas of unimaginable scale. The wonder is real and it is waiting. If this journey through alien skies has reshaped your sense of the possible, we would be honored to have you join us for the next discovery. Let us know in the comments which extreme world captured your imagination the most. Subscribe for more voyages into the mysteries of space, and as always, keep looking up.